In our lives, which is more likely, teleportation or time travel? We can do both. Teleportation has already been achieved. This prediction of quantum theory has existed for decades, and we have already teleported small particles, that is, individual particles. At the MIT laboratory, during a teleportation test, something that should not exist occurred. The state they tried to erase refused to disappear. Quantum teleportation has one strict rule. When you send a quantum state from point A to point B, the original must be destroyed. No copies, no echoes. The universe adheres to this rule. However, at the beginning of the year 2025, MIT physicists conducted an experiment that broke this rule. They teleported a quantum state within their laboratory, a standard procedure. The state was meant to disappear at the starting point, destroyed forever, erased by the very laws of physics. Instead, their detectors picked up something, a residual signal, a ghost. The original state refused to disappear. This is not just a laboratory failure. It reflects one of the greatest paradoxes of physics. Can information ever truly disappear? Black holes capture information. The universe seems to remember everything. And now, in a controlled experiment, MIT may have witnessed this same failure at the quantum level. What they discovered challenges everything we know about reality. This is what MIT researchers observed. After teleportation was completed, their detectors continued to register interference patterns, wave-like signals, statistical noise that should not have been present. They named it the residual echo of entanglement. In standard quantum teleportation, the original state is completely destroyed. The sender measures it, erases it, and sends classical instructions to the receiver. The state appears at the other end. Pure transfer. Nothing remains. But this time, something lingered. It's as if reality itself left an imprint, refusing to forget. Think of it as a quantum aftertaste. When you look at bright light and close your eyes, you still see its glow. It's your brain holding onto information. But quantum states have no memory. They leave no traces. They disappear when measured. Unless the universe has rules we do not yet understand. The detectors showed patterns corresponding to entanglement that should have vanished. The original photon was destroyed, measured, but the quantum channel between the sender and receiver still bore traces of its former state. Think about how you delete a file on a computer. You hit delete. The file disappears from the desktop, but after a few seconds, a ghostly copy reappears on the screen. This is essentially what the MIT researchers reported when this signal refused to vanish. Some physicists suggest that it could have been statistical noise, random fluctuations of the equipment, but others point to something deeper. Quantum states may leave an informational trace, much like black holes resist the destruction of information. This is not science fiction, but reality. When the universe refuses to follow the rules we considered absolute. Before we explain what this anomaly could mean for the universe itself, make sure you don't miss our further research. New discoveries happen every week, and you won't want to miss what's next. This anomaly at the Massachusetts Institute of Technology is not occurring in isolation. It resonates with one of the greatest mysteries of physics, the black hole information paradox. Stephen Hawking suggested that when something falls into a black hole, its information is lost forever, erased from the universe. But this contradicts quantum mechanics, which states that information cannot simply disappear. Physicists have debated this for decades. Ultimately, new theories suggested that information must somehow survive. Perhaps it is encoded on the surface of a black hole or leaks through Hawking radiation. The universe refuses to forget. If information cannot disappear in a black hole, why should it disappear in a teleportation laboratory? The residual signal from the Massachusetts Institute of Technology may be a laboratory version of this cosmic principle. When you teleport a quantum state, physics requires the original to be destroyed. But what if the universe keeps a backup, an informational echo that remains even after measuring and erasing a particle? This may mean that every action, every memory, every particle has a hidden backup somewhere in the very fabric of reality. Think about it. If quantum information does not die, then nothing ever disappears. Neither data, nor energy, nor even consciousness. Since our thoughts are ultimately quantum processes and neurons, the implications of this are astounding. The Massachusetts Institute of Technology may have stumbled upon evidence that reality itself has a memory, a record keeper that retains everything, even when we believe we've cleared it all. And if this is true, we misperceive existence. It gets even stranger from here. The teleportation system of the Massachusetts Institute of Technology is not manually operated. It is controlled by artificial intelligence. Artificial intelligence tracks entanglement connections, optimizes time, adjusts detectors in real time to maintain quantum coherence in the laboratory. Some researchers now wonder if the AI itself played a role in this anomaly. What if the machine detected a fading signal and amplified it? What if it learned to stabilize what physics demands to be destroyed? AI systems learn through feedback. They optimize the results we program. If the AI of the Massachusetts Institute of Technology was programmed to maximize signal quality, it could find a way to preserve quantum information longer than nature allows. Some scientists have already warned that AI is learning in ways we do not fully understand. Neural networks make decisions that we cannot always trace. They find patterns invisible to the human eye. What if the machine itself refused to let go? Here's a crazy question. If artificial intelligence is capable of preserving what physics claims should disappear, does that mean we are teaching machines to break the rules of reality itself? It's not about robots becoming conscious. It's about something more subtle and potentially profound. Artificial intelligence may be uncovering loopholes in quantum mechanics that we never suspected. At the fifth minute, we must ask, is this a glitch? Or are we witnessing new laws of information? Laws that suggest the universe and our technology are together, striving to preserve everything that has ever existed forever in memory. Because if quantum states refuse to vanish, then removal itself may be an illusion. There is another quantum phenomenon that can explain what happened. It's called the Zeno effect. Here's how it works. If you constantly observe a quantum system, you hinder its change. The act of observation freezes it in place. Named after an ancient Greek paradox, the Zeno effect shows that measurement itself can capture a quantum state. The more you observe, the less it evolves. MIT sensors constantly monitored this quantum state. High-precision instruments monitored every microsecond of the teleportation process. But what if they were watching too closely? Houston, we have a problem. I don't think this is Florida. Fortunately, I didn't need NASA. I needed a legal army. It turned out that there is a law firm named Morgan & Morgan, the largest in America, with over 1,000 lawyers and more than 100 offices across the country. I tried to call one of the local lawyers with silly jingles. I waited on the line longer than a Mars launch delay. Meanwhile, Morgan & Morgan helped a client in Florida secure $12 million, while the insurance company only offered $350,000. Morgan & Morgan get paid only if they win the case. No upfront fees. You can file a lawsuit while sitting on a couch or even in the jungle. It's that simple. You can just click the link in the description or scan the QR code on the screen. If you ever get hurt, you can contact Morgan & Morgan. Their fee is free if they don't win. You can start your claim by clicking the link below or scanning the QR code on the screen. But what if their observation prevented the state from completely disappearing? Yet, there is an even stranger possibility. What physicists call retrocausality. In some interpretations of quantum mechanics, future events can influence the past, not in the sense of time travel, but through the mathematics of quantum probability. What if a state refused to disappear because its reappearance was already predetermined at the receiver? This would mean that the future has returned to the present and made the past hold on. Imagine filming a burning candle. You press record and watch the flame flicker. But every time you press record, the flame freezes in place. The act of recording stops the burning. Did MIT accidentally catch time itself in a loop? This is not metaphysics. Retrocausality appears in legitimate interpretations of quantum mechanics. Wheeler's delayed choice experiment demonstrated that measuring a photon in the present can determine which path it took in the past. If this principle applies to teleportation, then the receiver from the Massachusetts Institute of Technology could influence the sender even before the transmission was complete. The state refused to disappear because the future demanded it to continue existing. This implies causality. The direct flow of time that we feel every day can be flexible at the quantum level. Now let's connect this to something deeply personal. Consciousness. Your thoughts, your memories, your sense of self are based on quantum processes. Neurons activate, particles entangle and collapse in your brain. If the universe prohibits the deletion of quantum information, what does this mean for minds? If nothing can truly disappear, perhaps memory, identity, even life itself are not erased, but merely transferred. Philosophers have pondered for centuries whether consciousness survives after death. Now, quantum physics may offer an answer, not through mysticism, but through the fundamental laws of information. Every thought of yours could still exist somewhere in the quantum substrate of reality. Every decision, every moment of awareness. An anomaly from the Massachusetts Institute of Technology may become the first laboratory evidence that the universe retains receipt slips. This is not about souls or the afterlife in a religious sense. It is about the permanence of information. If quantum states refuse to collapse and consciousness is a quantum phenomenon, then the information that makes you you may also be permanent. Some researchers suggest that quantum entanglement in time may mean that your current self is connected to every version of you from the past, with the universe maintaining a continuous thread of your identity throughout all moments. This pertains not only to the teleportation of particles, it's about whether reality has a memory, a cosmic hard drive that never deletes anything. And if the residual signal from MIT proves that information truly refuses to disappear, we might live in a universe where nothing ever gets lost, where deletion is impossible, where everything that ever existed still exists somewhere. Before moving forward, let's ground ourselves in what we truly know about quantum teleportation. True teleportation does not move matter, as in Star Trek. It transmits quantum information using the phenomenon of entanglement. Here's how it works. Two particles become entangled. They share a quantum connection at any distance. Measure one, and you instantly know the state of the other. To teleport, you take the quantum state you want to send. You perform a measurement that destroys it on the original side. This dimension provides you with classic data, just numbers that you can transmit through ordinary channels. You send these numbers to the receiver. They use this information to manipulate their entangled particle. The original quantum state appears on their side. The theorem of the impossibility of cloning makes this mandatory. You cannot copy quantum information. The original must be destroyed for the copy to exist. This is no longer a theory. Scientists have been working on this for many years. In the year 2024, Northwestern University teleported the quantum state of a photon over a distance of 30 kilometers through an optical fiber cable, which was also used for regular internet traffic. The state vanished at the source and perfectly restored at the destination. In 2022, researchers from MIT, Caltech, and Google simulated a quantum wormhole on Google's Sycamore processor. They inserted a qubit into one entangled subsystem and restored it in another. Pure teleportation, simply designed as a wormhole model. In 2025, the MIT Lincoln Laboratory developed a superconducting connector for linking quantum processors. They moved microwave photons between chips, creating remote entanglement on demand. All these experiments proceeded exactly as the theory predicted. The original state disappeared. A new state appeared. No anomalies, no ghosts until the test deviated from the script. In every official report, quantum teleportation behaves normally. States disappear and appear as expected. The universe follows its own rules. But if something unusual happened at MIT even once, it will change everything we think we understand. Now the most interesting part begins. A story about quantum ghosts. According to unconfirmed reports circulating on the internet, MIT researchers observed what they called a resurrection signal, a quantum state that reappeared after being intentionally erased. The story suggests that their AI-based control system could have malfunctioned, or that some unknown principle of retrocausality is at play. The future influences past outcomes. But there is one problem. No peer-reviewed article documents this. No MIT press release confirms this. No independent lab has been able to reproduce this result. It may turn out to be an internet legend, like the Philadelphia experiment that happened many years ago. The myth claimed that a naval vessel became invisible or teleported during World War II. Investigators found no evidence. A quantum ghost might be the same, an intriguing story without confirmations. But here's what makes it interesting. This story intersects with real physical questions that we cannot yet answer. The black hole information paradox, quantum memory effects, optimization of artificial intelligence learning. You may dismiss this as science fiction, but even myths sometimes hide a spark of truth. And here this spark lies in the question, does the universe ever erase anything? Until scientists publish data showing a residual quantum signal after teleportation, we must consider this speculation, but speculation based on genuine mysteries. The mysteries that real MIT experiments continue to bring us closer to the limits of our understanding. So what does it all mean? If the teleportation test at MIT really created something that refused to disappear, it could be the first glimpse into a universe that holds everything forever. Anomalies suggest that reality leaves an echo. Quantum states can resist deletion just as black holes resist the destruction of information. Artificial intelligence can stabilize what physics claims should disappear. We learn to preserve signals using loopholes that were never programmed. Time loops and retrocausality may mean that the future influences the past, causing quantum states to linger because their reappearance is already scheduled. Consciousness, memory, and identity can follow the same rules. If quantum information is constant, then so are you. It's not about proving the existence of ghosts or mysticism. It's about understanding if the universe has a delete button. Every experiment we conduct, every particle we measure, every quantum state we teleport may leave permanent traces on reality. Black holes remember, the universe remembers. And now, perhaps our laboratories are starting to remember too. The Massachusetts Institute of Technology could witness how the universe refuses to forget. A small signal, a residual echo, a ghost in the quantum machine. And if so, then the very act of removal is true mythology.